session 22. So 21 is about plane strain, 22 is going to be about failure criteria, which is going to be fun. Plane strain will also be a little bit fun. But before we do that, there were some questions about session 20 and the past homework. Okay, so let's see here. I think 20, there was a question about this one, right? Is this the one that some people are asking about? Yes.
It was, but I did manage to get it.
Okay, well, I see another nod. All right, so, okay. So here what we're saying is that sigma x, sigma y, sigma z, tau xy, tau xz, and tau yz, okay, all of these are equal to the same thing. All right, now your in Canvas probably gave you like slightly different numbers, correct? Did it or not? But in this case, it's equal to 100 megapascals, right? Or did it not give you all different numbers?
I think mine was like 92.
Yours is 92, right? Okay, but anyway, it's everyone has this number, okay? And so the process is to go about and calculate out these values. Right? Okay. And to whack it out like that. Now, what I'll say is this is a lot of calculating to do by hand. All right? And so this is what I would suggest. You don't have to do this, but I've already kind of given you some things, I think, to help here. So if we go to the website, and this is here, session 20. All right, and you go to the Colab here. And here, right, it shows you how to essentially run these problems, or this exact problem, right? So first I just hit Control Enter here, all right, and I go run anyway. And then we're finding the principal stresses for triaxial stress. So my case here that I just said is that they're all equal to 100. Okay, so 100, right? So I'll just copy. I'll even just make it 100 here. 100 here, 100 here, 100 here, 100 here. Okay? So they're all 100, and then I hit Control Enter. And that's the answer. The principal stresses are 300, 0, 0. Okay? So what's interesting about this? Can we see a pattern? Let's try 150. Or maybe 150 is fine. 150, 150, 150, 150, 150, 150. I hit Control Enter, I run it, I get 450, 0, 0. So what's the pattern that we see here? Yes?
It's 3 times whatever your initial number was.
Right. So if you are given an element where all the stresses, all 6 stresses are the same value, it has this unique property of coming out with one principal stress. I don't know what the orientation is, but one principal stress, right, that is going to have be 3 times those values. Now these two methods. Now this. Remember we said there are kind of 2 ways to try to skin this problem. One is to use the eigenvalue solution, all right, and so you create this array and do that. Or you can find the roots, so this thing called np.roots on the coefficients. You notice that the outputs are slightly different in terms of the order. In this case, 0, 450, 0 versus 450, 0, 0. But essentially, what we have here is that the largest one we would call sigma 1, and then the other two, sigma 2 and sigma 3, we say are 0. Okay. Any questions on that? Okay, so if you're getting jammed, all you have to do is hit Control Enter on the collabs, and they run. Okay, or you have to enter the right numbers. Something, it's not for all of them, but I do suggest that you take a look. All right. Okay, so now the other question. Was I think this one? Yes, and so I had scribbled a bunch of things here. Okay, and people were talking about doing the eigenvalue thing, all that kind of jazz, right? But let us take a step back. Okay, and if someone could give me their sigma x and their tau xy, I'll try to do the problem real time. But I need you to at least give me your sigma x and your tau xy. What did you all get? So someone gives value for sigma x and tau xy. Now, of course, maybe not of course, sigma y equals 0, sigma z equals 0, tau x z and tau yz are equal to 0 as well. But someone want to give me values? Sure.
For sigma x, I got negative 41.1.
Okay.
And then for tau xy, I have negative 2.55.
Negative 2.55?
Yeah.
Okay, so we'll just call negative 2.6, okay, and negative 41. So did a lot of people get like negative numbers for these? All right, that's okay. Now remember that the rest of these, sigma y, sigma z, tau x z, these are all equal to 0, okay? So if I draw the Mohr circle, where am I going to, what's my approach here? What do you think my approach should be? Eric, you're smiling, so go ahead. Give me some love here. Or
After
give me
the
some.
test point with negative 41 on the sigma side, and then
Okay, so I could do it that way. Sure, fine. You want me to do that? So where is it? That's like over here, right?
yeah, I work best visually, so for me it's real easy just to.
Okay, so we'll say that's going to be our sigma x tau xy, right? Okay, now what else?
Find the average, define the midpoint.
Right, so the average would be like minus 20.5 or something like that, right? So we'll say sigma average is minus 20.5, 21, whatever, something in that ballpark, right? So that's going to be, halfway, right, around there. Okay, and we can call that to be the average. Okay, what's next?
Calculate the radius.
Okay, so yeah, we can calculate the radius if you want. That's fine. We can do that. Oops, that's not the bestest. Okay. So how do you calculate the radius?
It's the square root of. I forget what it is offhand, but
Yeah. So, well, let's just you don't have to just tell me what to do. You don't have to know the numbers. Just tell me what to do.
so it's sigma x minus sigma y over 2 squared.
Okay. So can I say that this distance right here is going to be the sigma x minus sigma average? Is that okay? Are you okay with that? So let's just do it that way, right? And squared, right? And then this y is this tau xy.
Plus that squared. Yeah.
Okay? So that's the radius. Okay, so now everything else is, so if I were to draw this circle, you know, I can kind of do it like this, but I don't like doing this, but sure, I'm going to do that first because I feel more comfortable with that, right? We know that this sigma y is equal to 0, right? This sigma y is equal to 0, so this other point has to be on the tau axis, all right? So for me to draw my circle, it's going to look like that. Does everyone agree with me on this? Okay. And this problem is asking, what is it asking actually? I don't even know. What did I ask? Oh, absolute maximum shear stress. Okay. So absolute maximum shear stress. Okay, so so I have another point, well, I have a sigma 3 is equal to 0 at the origin, right? So if I'm thinking about absolute max, I've got one circle in here, right? That makes it wherever this hits over there. And I've got another circle that kind of comes, you know, from this point here to that. But I'm just interested in the absolute maximum shear stress. So what is absolute maximum shear stress going to be? Yes, Andrew.
Just the radius?
Yeah, it's just the radius. Okay.
Yeah, I actually had a question too. So how do you know that sigma 3 is equal to 0?
I'm just putting this out as, hold on. Okay, how do I know it's equal to 0? That's a very good question. How do you think I know it's 0? I'll ask you. What would be my reasoning? Yes, Josh.
Is it?
Huh? Oh, go ahead. Go ahead.
Is it because, okay, so sigma z is equal to 0, but is sigma z equal to sigma 3?
It is, but it's more than that. It's because sigma z is equal to 0, and tau yz is equal to 0, and tau xz is equal to 0. Okay? This is what we've been given is a state of plane stress. Okay? Remember we said that these are the only two calculations really that have to be done. Everything else is going to be equal to 0. Okay? And so once we make that assumption, once someone says plane stress, then immediately you know that you can only rotate about the axis normal to that plane stress, and that is where you'll find the principal stresses. Okay? Because the sigma 3 is going to be 0. Does that make sense? Right? Because there are no shear stresses in the other dimensions, and the normal stress in the other dimension is 0 as well. Right? So that's why if we only care about what's happening in the plane in terms of being able to find the max. Okay? Now, that said, right, in this case, the maximum in-plane shear stress ends up equaling the absolute maximum shear stress. Okay, did you hear what I said, right? In this case, the maximum in-plane shear stress equals the absolute max. But that doesn't necessarily have to be the case, right? We have examples where it's definitely not the case, primarily when we're doing the loading of a pressure vessel, a cylindrical pressure vessel, not a cylindrical pressure vessel, not a spherical one. Okay, well, even a spherical one too, actually, right? Both of them, right? Because let's just think about cylindrical pressure vessel. Right? We're going to have a sigma 1, a sigma 2. Well, let's see. Sigma 1 is going to be 2 times sigma 2. Okay? Or, sigma x, maybe you can say whatever, is 2 times sigma y. Or even you can say sigma y is 2 times sigma x. However you've got it defined, right? So when you start looking at the Moore's circle for these types of systems, right, what you see is boom, boom, and then the third one is right there. Okay? And so in this case, it's not the in plane that's the maximum. It's this other, like, this would be like a 1, 3, okay? That's going to give you the, a tau 1, 3 that's going to give you the absolute max of shear stress. Okay, does that make sense? Okay. And then, like we were saying yesterday, for the spherical one, we just have sigma 2 equals sigma 2. I mean, people write it different ways, but that is just like this, you know, sigma 1 equals sigma 2. I mean, I guess we can write it that way, equals, and then this is sigma 3, okay? And so before it was just you're at a point, essentially. Anywhere on that plane, you rotate about a radius coming out of the sphere, and you rotate it, and you're just still there. You got two axial stresses that don't change as you rotate about that normal component. But you have to look out of plane. You have to consider what's happening in the direction where you have a sigma 1 or sigma 2, 3. You have two planes to choose from, essentially. And that is where you're going to have your absolute maximum shear stress. Okay? Questions on this? Thoughts? I'm open to you. Do you want to clarify what I've said? Maybe it's not clear how I've presented it. Any other thoughts? How would you think of this? How are you thinking about this? It's a little tricky the first time. Okay? It's a little tricky. But you'll have more chances. Get it? More. Alright, that was bad. Okay, so let's go ahead and move on to, man, tough crowd. Alright, let's go ahead and let's move on to plane strain. Did I hit it? Okay, so for plane strain, we're going to discuss essentially how we do transformations. We're going to make a case for using Moore's circle again and discuss how this relates to planar stress, planar strains. Sorry, and we'll also talk a little bit about the utility of using these transformations for making measurements. Okay. Anyone use strain gauges before? No? Yes? No? You?
We learned about physics and we used like a little demonstration.
Okay, great. All right. Anyone else? All right. Okay. So, what do you think a strain gauge does? Yes.
It tells you how much strain happens on an object.
That's right. And it can only tell you on the surface, correct? And it will tell you in a particular direction. Or it might tell you in 3 directions, depending on how the strain gauge, and they're called rosettes, are set up. Okay? So first, let's talk a little bit about plane strain and how it relates to what we think about with plane stress. Both of these words have the word, or both of these phrases have plane in them. All right, so we're thinking 2D again. And the difference here is that plane strain we visualize in terms of a thick plate. Okay, plane stress we're thinking, oh, it's just a thin wall of a pressure vessel. That's the plane stress. Okay, and stress in sigma z and tau xz and tau yz are equal to 0. And here, in terms of the variables that we write out, it's the same dealio, all right? Epsilon z is going to be equal to 0. Gamma xz is going to be equal to 0. Gamma yz is going to be equal to 0. But for this scenario, physically, we are typically thinking about thick plates. Now, we're going to kind of stretch this a little bit and come back down to like thinking more about it in kind of thinner scenarios, and then using kind of more circle and more circle for plane stress with more circle for plane strain. And so sometimes we kind of violate some of these conditions, but the general idea is that this is going to be a thick plate. And why and how is that so? Well, if you begin to think about how you could have a situation where you just have like an epsilon x, all right, or you have an epsilon x and an epsilon y. It needs to essentially be infinite in that thickness, all right, such that you don't have a strain in one direction influencing a strain in another direction. Like, if I have epsilon x, right, and I want my epsilon z to be equal to 0, right, so I do epsilon x, a real material has a Poisson ratio. Okay, and so that means it's going to cause there to be contraction in this orthogonal direction. Also would be contraction in the y as well, okay? So, but if we just think about the z direction, we're typically thinking it has to be really thick to minimize the effect of the Poisson effect, the Poisson's ratio, okay? So they're generally thick plates. And this is going to, quote, focus our attention on a body whose particles all lie in the same plane and which deforms only in this plane. Okay? So if we make it super thick, we can think about, okay, yeah, there could be an effect in the y, but we don't want it to have an effect in the z. Okay? And if we have an epsilon x, right, it might look something like this. If we have an epsilon y, it might look like something like this. And if we have a gamma xy, right? Now remember, and we said before, right, before we were kind of saying, hey, you can kind of think of a shear stress causing a shear strain. It causes the element to kind of deform like this, right? And we were saying that this is going to be some delta here, and this is going to be some dy, right? And that the angle in here is the angle we care about, and so the tangent of that gamma was going to be equal to delta over dy, right? Remember we said that? That's how we define, and then we said gamma is just going to be approximately equal to, because it's a small angle, can't write, delta over dy, like that, right? We kind of said that earlier. Well, I also kind of said that's not completely how people in mechanics write it out. Usually what they do is they say, actually, this deformation comes off of this axis as well, the horizontal one here. And yeah, you have a an internal angle here, okay? And essentially you have half of the gamma and half of the gamma over here, okay? And another way to write it is that the gamma xy is equal to pi over 2, so 90 degrees minus whatever that internal angle is. Okay? And so that's kind of the more proper way to think about the shear strain. Okay? So we are going to be thinking about epsilon x, epsilon y, and gamma xy. And that's, right, we were just talking about how do we know, right, that sigma 3 is equal to 0? Or how do we know that sigma 3 is equal to sigma z is equal to 0, right? Andrew, you were just asking that question. Well, it is because the other kind of slots in that tensor are equal to 0. The tau x y, the tau x z, the tau y z, the sigma z, right? All those were equal to 0. Okay, so similarly, right, we're going to be drawing these planar elements just like we kind of drew them for plane stress, right? But we're going to be thinking about them in terms of strain. Okay, so right, plane strain, thick, plane stress, thin. Okay. Now, when can plane strain and plane stress be equivalent? And this is maybe a little brain teaser. It's the case when the Poisson ratio is equal to 0. Okay, what are we talking about? So epsilon z equals 1 over e, this jobby, right? Remember this? We've all seen this. We all love this. Well, maybe we don't love it, but we respect it, okay? So when the Poisson ratio is equal to 0, look what we get. Boom, da-da-doo. This disappears. And so then we just get epsilon z is about equal to 1 over e times sigma z, right? And that's the first Hooke's law that we've introduced for axial loading, okay? So this is a case when the plane strain and plane stress could be equivalent. Does it exist? Not really, okay? You know, real materials are going to have a Poisson ratio. So it's nice, but it's kind of this ideal. Nonetheless, we're gonna, like we said, we're gonna bend the truth a little bit here to make things convenient for us in a little bit. So normal strain, kind of a review. This is a review. This is strain represents the displacement being particles in the body relative to a reference length. So we've seen this before. I think I've shown this slide multiple times now, right? Where we have some delta x and we have some dx, and that's the epsilon xx, and we just say epsilon x, right? We don't repeat. Epsilon yy, right? Epsilon y would be the delta in the y direction over dy. Okay, and then shear strain, right, is, like we said, this is how we think about it with this delta, tan delta, all this stuff, right? And then normally the way that's kind of more rigorously defined is that you're thinking about what are this angle here and this angle here above that you can add up to be equal to the gamma. All right, or you do pi over 2 minus this internal angle in the pink to figure it out, okay? Don't worry, you're not going to have to really do this, okay? I mean, we need to know what these strains are, but in practice, we're going to pretty much just say, use more circle, okay? And think and remember what these bits mean, kind of in this general sense. And frankly, I'm more comfortable calculating stresses than afterward calculating out the strains, okay? But there are situations where you have a strain gauge, and so you're going to be given strains, and you need to then figure out the states of stress, okay? So if you like, you can take a look in Hibbeler's book, all right? Or you can click on this link if it's still there, and you can get these derivations, okay? What do these look like? These look extremely similar to the set of transformation equations we had for stress, okay? Now, I wouldn't expect you to get this without, looking at it essentially, but there's one big time difference, okay? Where is this big time difference? There's a factor of 2 in the equations, okay, for plane stress and plane strain. Where is this factor 2? Dum-ba-da-dum, right there. Remember, what would have gone in there? If this were to figure out a principal stress, sigma 1, sigma 2, this would be the same, except we have sigma x plus sigma y over 2, right? That's the average. This would be the same. That's the square root of this component under here, right? That'd be sigma x minus sigma y or sigma minus whatever. But this would be just a tau xy squared, right? We just kind of did this a few minutes ago when you had that problem for that was number 6. So this gamma xy over 2 ends up affecting a few different things. It affects the Moore circle that we do. And do you remember in the world of pre-POMAX, right, when we did the finite element, we said, hey, it's spitting out values that are not the true shear strain. I don't know. You remember that? I said, look, it's like half of the true shear strain. That was like the E12, E13, E23, okay, in pre-POMAX. And why? That's because when you do this math and you do these transformations and you do the rotations of the tensors, it's dealing with these half values, okay? And so it is something that we have to keep in mind. So tau xy, these are the substitutions essentially if you want to make them. Going from the equations that we had for the plane stress transformations to the equations for the plane strain equations, you just do all the normal components are just essentially flipping, or the sigma for an epsilon, except for the tau and the gamma. Okay. Any questions on this? All right. So, yes, you can use these equations. All right. No, do I emphasize plane strain on exams? I don't know. The only thing I've asked with plane strain has had to do with strain gauges. Okay, so maybe this time, maybe you all will be fortunate that we come up with a fun plane strain problem, but I typically don't emphasize this that much. All right, there's more things there are other things that I think are important. Well, let's do an example. I see some people writing, but I think, okay, you stopped. All right, so let's do an example. What is the state of strain for an element rotated 45 degrees from a condition of uniaxial strain, epsilon x? Okay, so what does this sound like? Uniaxial strain, epsilon x. This sounds like a tensile test. All right, so now we say, hey, let's do 45-degree rotation. So epsilon x prime, blah, 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 all these things. So, 45 degrees cosine of 90 degrees, that's going to be 0, right here. So this term's going to disappear. Sine of 90 degrees, that's a biggie, right? But gamma xy was equal to 0, okay? So it's going to just keep this term. So epsilon x prime is going to be equal to half of the epsilon x, right? Epsilon y prime is going to be equal to half of the epsilon x because, once again, sine of this is 0 and this cosine of 2 theta is 0. Okay, but this will be interesting, right? So we have gamma x prime y prime over 2, and then we got our negative of this guy, but epsilon y was equal to 0, so it's going to be it's going to be half minus epsilon x over 2. That's going to be half. Sine of 2 times 45, that's 1. Okay, so we keep this. Cosine times 2 of that goes bye-bye. Right, but gamma xy was 0 anyway, so it didn't really matter. Okay, so we can do all this out. Okay, and we get that epsilon x over 2 is that. Epsilon y is going to be that over 2 as well. And then we can calculate the gamma, all right? And I made, once again, I didn't say this quite right? This is half over here on the left side, and it's over half here, so it's just equal to minus epsilon x, okay? And what does this look like? Well, we have, all right, something being stretched out like this, but then we rotate it 45 degrees, and we want to look at what is the strain, what's happening with the strain. So this is the element, it's expanded a little bit, all right, because it's got a gamma that's negative, okay, and we have this epsilon x over 2 dx prime, okay, well, an epsilon x over 2 dy prime. So you see that it's also strained a little bit like that. Okay, so that's what it looks like, which is a little bit counterintuitive. Okay. It was probably, I don't know if it's simpler to think about the stresses, maybe. It's probably simpler to think about the stresses because when we, remember we did slicing for the stresses. Okay? For the stresses, we were able to solve equilibrium. Here it's a little bit different, right? We're looking at, you can look at the derivation, but here now we're looking at strains, and at their root, it's not like I mean, yes, you have equilibrium, I guess, back in there somewhere, but here we're looking at what's happening to the displacements more than the equilibrium and the stresses. Any questions on this? So if I were a very good professor, right, what I would have is kind of a rubber bandy thing, okay? And I would draw on this rubber bandy thing, I would draw a box, right? And I would stretch the box, and along the axis, all right? And then I would draw a diamond that's, or essentially the box rotated 45 degrees, and you would see, oh, that diamond is going to stretch. Okay. Out a little bit. Okay? So like, I can do that. How can I do that? Let's see. I wonder, maybe I can do it actually. Let's see. I can do it in the virtual realm. All right? I can do, here's my box, and here's my diamond. This is unrehearsed, by the way, so I don't know if this is going to work or not. Okay, but I think maybe the power of PowerPoint will work out here. Okay, so if now I make this a sample where I'm pulling, with a force to pull this piece apart, okay? So now the moment of truth. Whoa, okay. All right, so you see that? That stretched, and that kind of stretched and became a little bit more squished. I know. It doesn't have the Poisson effect though. If I want to do the Poisson effect, then I got to do this. There, right? There's the Poisson effect as well. Okay, you're not impressed. That's fine. That's okay. All right, another example. What is the state of strain for an element rotated theta from a condition of normal strains of blah? So 10 microstrain and epsilon equals 20 microstrain. So microstrain, right? That's just 10 to the minus 6. We've done this before. We've talked about microstrain. Megapascals, microstrains, right? These are kind of the flipped, right? Kind of ideas. Mega is 10 to the 6, micro is 10 to the minus 6. And it kind of makes sense because you have a sigma and that's equal to, 1 over, it's equal to E epsilon, right? And E's, I don't know, maybe that doesn't really, E's typically 10 to the 9th. That's the ratio that we typically see. We're dealing with microstrains and megapascals. And typically, like 100 microstrain maybe is in that realm, like 100 megapascals, right? Those types of things, they work out. Okay, so what is the state of stress or state of strain here? So once again, we can write out the nice formulas. And we say, okay, here's the epsilon x prime, putting these numbers. Okay. Hold on a second. Yes, is this right? Yeah, 10 plus 20 divided by 2 is 15. Good. Okay, 10 minus 20 divided by 2 is negative 5. Good, yeah, these numbers are right. Okay, and gamma x prime y prime is equal to that. Okay, so the original would have been something that was kind of maybe stretched maybe twice as much in the y as it was in the x. You see that? That's me, again, doing a little sketcheroonie. Okay? And then what we want to do is we want to rotate this element. Okay? And what are we doing? We're rotating it some arbitrary amount. So if you wanted, you could say, okay, here's the original element, and now I've rotated it by this amount theta. Okay? And what are we doing? We're looking at the resulting, and this is of course super exaggerated, okay? But this is the resulting deformation of this element that's been undergoing some strain. And we had an epsilon x prime dx prime. We had an epsilon y dy prime, right? Those are just the displacements of this element. And now we've figured out, okay, our new epsilon x prime, okay, is going to be this value. Our new epsilon y prime is going to be this value, and then we have a gamma x prime y prime over 2, all right, which we can describe as these angles exterior to this this internal one that we have here. Okay, so again, just trying to give a little bit of perspective in terms of what this actually looks like, okay, what these transformations look like. Yes.
I think the first set of addition and subtraction in dx prime and dy prime were flipped.
Oh, did I flip them? Let's see.
It's -5, so it flips the sign.
Yeah, yeah, right. This is -5. This is right.
Oh, okay.
It's 10 minus 20, and this is 10 minus 20 minus that. Okay? Thank you for keeping me sharp, or keeping it sharp. All right. Keeping it honest. Not that I would have ever made such a mathematical mistake before. Never. No, I did actually. The first time I put it out, it's just like, okay, sorry. Okay. All right, so relationship between G and E. All right. So here is our element. This is one way of looking at the shear strain. All right, we talked about this. Maybe slightly, slightly not coolish to make this the horizontal, but this is the nope. This is not. This is not correct. The gamma's in here, right? Okay, and this is the material element. Okay, and we have a Hooke's law for pure shear. We talked about that before. But we never, and we talked about the shear strain curve, okay? But we didn't derive the G is equal to E over quantity 2 times 1 plus nu. Wait, here we go. If we start with an element in pure shear, okay, it looks something like that. Then we rotate that element by 45 degrees. Well, what happens there? Well, we use more circle, okay? And you're like, wait, you just said we were doing transformations with a thick plate. Now you're telling me we're doing transformations with a thin plate and plane stress. I'll be like, yeah, whatever, okay? So we're rotating this element by 45 degrees, right? At this point, this is, I don't know, the bullseye, or I don't know, target practice, I don't know, crosshairs. Okay, that's what you get in your head for pure shear, okay, and when you're dealing with stress. Okay, so you're going to have when you rotate by 45 degrees, from pure shear, you're going to have one normal stress that's positive, one normal stress that's negative, and they're going to be in opposite directions. Okay. and that's what you have. Okay, so now if I draw that element, okay, this is what it looks like. And to be careful, right, I guess I could say, we started, just a note, right? We started here and we moved this direction because we rotated by 45 degrees and we did, sorry. Yeah, that's right. We started here and we rotated the element by 45 degrees and we rotated on Moore's circle by 90, right? Because it's 2 theta. Okay, now we use this equation, this handy dandy one, right? Which is truth, okay, for epsilon x. And then we substitute in using what we had for our sigma x, okay, and our sigma y, okay. And this is maybe a little counterintuitive because this was sigma x, right? But we said that sigma x is going to be this tau xy, sigma 2 is going to be this minus tau xy, right? This is, you could say this is our new sigma, this is our new sigma x, this is our new sigma y, or this would be the sigma x prime and sigma y prime. And I plug these in, okay? So now we have an expression for epsilon 1, okay, is equal to this. And we have our strain transformation equation. And we can say that epsilon 1 is equal to gamma xy over 2. How does that come to play? Well, here's epsilon 1, right? Epsilon x plus epsilon y, okay, over 2. So if you plug these guys in, all right, we get this. Or we can look back to what we were talking about previously, but epsilon 1 is equal to gamma xy over 2, and tau xy is equal to g gamma xy. So now we can write out this expression, right? So this is the epsilon 1, right, is equal to epsilon 1, right? This is equal to this, okay? That one to that, and then to that, all right? And then we have this expression. So now we plug in g gamma that, all right? And and then you see, okay, g gamma this, right? So this is just going to be the e over 2, and we get g is equal to e over 2 times quantity 1 plus nu. So this is how we can derive. We've already been using this relationship for the shear modulus and the elastic modulus and the Poisson ratio, and now we've kind of done this quick derivation showing it to be the truth. Okay. One of the questions you'll get to do on the homework is essentially just applying these equations. All right, so that should be straightforward. I think, let me see, I don't know. Let me see if I did it or not. I just want to see if I was kind. And if you're like some folks, you can make sure that my equations are correct. Oh, this is sad. Okay, so I didn't create a collab for this one. All right, at least I don't have it here. Okay, but yeah, did I not? I guess I didn't have time. All right, I must have not had time to do it. But you can use collab, all right, if you so desire. You don't have to, but you can. All right, here we go. Part 2. More circle. Well, the big difference the only difference See, you can see I even kind of cheated. I had one of my old Moore circle, and I had like changed all the values, okay? But not that one. That was a mistaker, okay? So really, the only difference is that instead of tau axis, you have a gamma xy over 2 axis. That's really the only difference. Okay? So we just have to be a little bit careful there. So again, this is more circle for plane stress, but we can also use plane, remember Moore circle is just an abstraction, okay? That abstraction being, there are the transformation equations, and I found a circular, or Moore found a circular pattern, right, that can fit these transformations. So again, it just makes sure that gamma xy over 2 is this y-axis, or the vertical axis, and epsilon is the x, or the horizontal axis. And once again, you would plot the middle point of the circle, using the average of the normal stresses, but normal strains now. You can figure out where a point is, like this, if you know the gamma xy, and you can make a circle with the appropriate radius, and you can figure out that radius by figuring out, okay, what is the adjacent side and what is the opposite side. It was years before I understood what the adjacent and opposite side were. I think that when I first learned it, I don't know, do people think about adjacent and opposite? Okay, that's good. I was like, what are they talking about, adjacent, opposite? Okay, I guess it's because I'm simple-minded. But, the adjacent being the side of the triangle that it's next to the theta, right? And the opposite being the one that's far away from it. Okay. All right, so, yes. So, a question here, all right? So, for the homework, okay, you're going to have some type of epsilon x and epsilon y and gamma xy, right? And just make sure you divide, the gamma xy by 2 when you draw it out, okay? And you'll have a fun time figuring out what the largest principal strain is. What is that going to be? Well, if I had these values, right, epsilon x, epsilon y, okay, I am going to figure out where the average is, right? So the sigma average, that's when I'll use both of these right there, okay? And I could choose, right? I could choose to plot, a point over here, which is maybe less common, where I'm looking at, okay, that's where my epsilon y and then negative gamma xy over 2 would be. Or I can choose the point, plot a point that's over here, which is going to be my epsilon x. Oops, I lost my mouse. Epsilon x, right? And then that's going to be straight up gamma xy over 2, not negative of it. Okay? Any questions on this, or am I going too fast? Okay? Yeah. All right. So this is going to be an opportunity to do more circle. Okay, and then find the absolute maximum shear strain. Same dealio. Just make sure that we collectively look at gamma xy over 2 instead of gamma xy. I can essentially assure you that the probability of 14 people doing this type of problem and one person forgetting that it's gamma over 2 is probably like 99.9%. Okay, yes?
So when you say gamma over 2, is that like when you're plotting the point to EX?
That's right.
X, Y, or Z?
Yeah, so you're going to plot it, and then when you look at where your circle goes, you're going to get a gamma max over 2, and so in the end, you're going to multiply by 2. Okay, so you do the whole thing, all right, with this divided by 2 factor, and then at the very last step, or the very first step and the very last step are to put in that factor of 2. Yes?
In order to record everything on the chart as gamma over 2, do you have to divide your gamma value, your initial one, by
Yeah, that's what we're saying. The first and the last thing you want to do is divide by, or the first thing is divide by 2, and then the last thing is multiply by 2. If you're interested in the shear strains, or if you're dealing with shear strains. Okay. If you have a happy-go-lucky problem where it's like, hey, here's epsilon 1, or here's, I don't know. That's probably no. Yeah, here's a happy-go-lucky problem. Here's epsilon 1, or here's epsilon x, here's epsilon y. The shear strengths are all equal to 0. Tell me what the no, you still have to multiply by 2 in the end. If you want the absolute maximum shear stress, or absolute maximum shear strength, I don't know. I'm trying to think of a problem that would be interesting. Yeah, I mean, yeah, you kind of have to keep track of them. All right. Okay, and then the last part of this is strain gauges. Here's a strain gauge. How does a strain gauge work? What do you think? How does a strain gauge work? Or how does this type of strain gauge work, I should say?
Let's go to the change in the resistance of the material.
Yes, okay, so there's a change in resistance in the material. What is inducing that change of resistance?
It's the elongation of the material thins it out, and then, it resists.
Yeah, so if okay, so good. If I change the cross-sectional area of a material, what happens to the electrical resistance? If I make that cross-sectional area smaller, what happens to the resistance?
Goes down, increases.
It goes opposite, right? The famous pipe hose problem, right? If I have a hose, right, and I make it narrower, right, because everyone here is a mechanical engineer and we like fluids more than we like electric current. I don't know. Maybe some of us do, maybe some of us don't. All right, but anyway, you make that hose, you make that hose smaller in diameter, or you stomp on it. All right, and the classic thing is, whoa, look, now it requires more pressure to maintain that same flow rate. Same thing is true for charges in the wires. Okay, if you reduce the cross-sectional area, it's going to have more resistance. Now, it turns out that's not completely, it is true, okay, this is true, this is truth, and I like to think, oh, it's just so simple. The resistivity stays constant, the cross-sectional area changes, and the resistance changes, okay? But and so then you have what's then you have what's called a gauge factor, which is the ratio of change in resistance divided by the strain. Okay, and so this does have an effect, right? But it turns out that this gauge factor, okay, is going to also be affected by a change in resistance. Okay, over rho. Okay, so I'm sorry, a change of resistivity over rho as well. So the material itself also responds somewhat to the strain. Okay, so it's not just this cross-sectional area. Okay, usually. And I try to think of it just so nicely that it's just the cross-sectional area change, but you should know that these materials the materials of choice can have a piezoresistivity to them themselves. Okay. Now, regardless, if you see you see the path of the electrode, it goes back and forth, back and forth, back and forth. Well, the reason it does that is because the longer, the more wire you have experiencing this, and the more wire you're stretching in series, so these are essentially wires in series with each other, the larger the effect is going to be. Okay? And you don't necessarily have a huge object that you're applying the strain to, right? You don't want to just have one long wire, right, going across. So it's clever that they do the serpentine pattern. Okay. So that's if you look at it, and you'll do labs later, okay, where you use what's called a Wheatstone bridge, and that's probably what you did when you were like, they were telling you how to measure strain. Okay, anyway, but there's some tricks you play with the electric circuit so that you can, in fact, measure this change of resistance and be able to figure out what the strain is. Now, notice, this gauge is only meant to measure, well, how do I say this? Yeah, it will tell you the strain in which direction? This direction. Okay, now you could apply strain, you know, in the orthogonal direction to these lines. Okay, and then will there be some small effect? Oh yeah, there will be, right? Because like you're causing, you know, those things on the top and the bottom, right? It might not be measurable, right? But this is designed, right, to measure the strain in one direction. So if you want to capture the state of stress in a plane, what do? You orient these strain gauges in different directions. Okay? So this one, the one here, the one gauge, okay, is going to be telling you the strain in the x direction. The 3 gauge is going to be telling you the strain in the y direction. And the 2 gauge is going to be telling you the strain in the 45 degrees. Or the one on the left, A is minus 60, or however, yeah, minus 60. B is in the x direction, and C is positive 60. So these are kind of the two common strain quote rosettes, okay, that you'll find. And the rectangular rosette, okay, is the one in the bottom. Why? Because this one is at 90 degrees, okay, relative to the other. So this rectangular one, okay, is going to have epsilon A. Everyone see this? Epsilon A is essentially equal to epsilon X, okay? And if we use the well, let's just use this equation, right? You see this equation right here? Yeah, I was looking for it. Theta is equal to 0, right? So this is 1, so this is going to be epsilon x minus epsilon y over 2 right here. Theta is equal to 0, this is 0, right? And, well, this is just the average. That term right there is just the average, right? So epsilon A is equal to epsilon x. Does that make sense? Yeah. So epsilon B, okay, is going to be plugging in theta equal to 45 degrees. Well, that would be 90 degrees, right? That's going to be 0 then. But then we have this equal to 1, so now we capture a component of gamma xy over 2. And we still have the average. So this comes out, epsilon b is capturing effects from strain in the x direction, strain in the y direction, and the shear strain. And then epsilon c, what do you guess? What is epsilon c capturing? Or, huh? Yeah, it's just telling us the epsilon y, right? It's just, all it is capturing what's happening in the, in the y direction. So now I can rewrite this gamma xy, right? So I've got epsilon b, right? Epsilon a, epsilon c. I can reorganize this and, okay, well first, if I want to know the strain in x, I just look at epsilon a, right? If I want to know the strain in y, I just look at epsilon y, all right? But if I need gamma xy, I have to use information from all 3 gauges, right, in here to figure out what it is. Does that make sense? Okay. So it's pretty. These are useful tools. It's just some practical things. They're a pain to get right. Okay? And you're like, why don't I see products with strain gauges on them all the time? Well, it's because one, they add weight, they're expensive, they can be expensive. But 2, if you ever play with strain gauges, you've got to use the right adhesive. Okay, you gotta make sure that you get it nicely coupled, that the strain gauge is not slipping relative to the top surface. And then you've got this idea, oh, well, if I make a strain gauge too thick on top of it, right, I could be affecting the strain itself. So typically these strain gauges are supposed to be kind of, not very thick, right? And we were just spending all this time telling you how plain strain is on thick, substrates. Well, you want whatever you're measuring to have a high stiffness relative to the strain gauge itself, right? The strain gauge just is supposed to be along for the ride. Okay, so now what about the strain gauge where you have the 0, 60, 60? Okay, so epsilon b, yay, okay, is equal to epsilon x. Okay, strain gauge A, theta is equal to minus 6 degrees. Yuckiness ensues. Okay, you see that? And for strain gauge C, again, some moderate yuckiness. All right, that's not a very technical way to describe this, right? But it doesn't work out as nicely. I don't think I've ever asked an exam question to use the 60 degree 0, 60 degree strain gauge. Okay, but you get the idea, right? And once again, I can solve, okay, for the different strains. I want to say stresses. The different strains in the system if I have values from all three of these. So here comes epsilon y, and then gamma xy is going to be this expression right here. Okay? So what is the point here? I'm looking for three parameters, right? Epsilon x, epsilon y, gamma xy. So each one of these strain gauges only measures reliably in one direction. So I need, for three unknowns, I need three sensors. Pretty straightforward. Okay? And it's useful, right? Because then I may not really care about the strain that much, but you know what? I probably care about whether my structure is going to fail. So I can relate these strains to the stresses, right, through these other transformations that we've described, right? The epsilon x is equal to 1 over e times the quantity sigma x minus nu quantity sigma y plus sigma z, for example. I can use those relationships, those constitutive relationships, to figure out what the stress is in the system. Okay? Now, I could also know, hey, if I'm experiencing that much strain, then I'm probably failing my material. That's another way to do it, right? Because I could look at the strain, the shear strain, or I could look at the strain, just the stretch strain plots, okay? And know, oh yeah, if I have that much strain, that's axial strain, or if I have this much shear strain, then whammo, I know where I am on the stress strain plots, or the shear stress shear strain plots, okay, and I've got problems that I can address that way. Okay, yes, so here you go. A question, all right, that says we are measuring the strain on a cylindrical pressure vessel with rectangular rosette, where the A gauge is aligned with the longitudinal direction and the C gauge is aligned with the hoop direction. All right. So if the hollow pressure vessel has internal pressure P, radius R, and wall thickness T, elastic modulus E, and Poisson's ratio nu, what do we expect reading on the V gauge to show? So that the opportunity, right, is to use what we just discussed, plus these relationships that we've loved from the past to be able to figure out what strain gauge B is experiencing. All right, so we've talked about plane strain, what it is. Okay. We've talked about Moore's circle with using plane strain, and we've done an example that's relevant to structures that uses strain gauges. Okay. Any questions? All right, excellent. Okay, you can take a stretch. I'm going to go ahead and get the next session up.